to section 1 of chapter 13, focusing on advanced derivative concepts. We're going to now move beyond just polynomials, and we're going to derive the derivatives, no pun intended, of the sine, cosine, natural log, and e to the x functions. And to do that, we're going to use our first principles, but we're also going to use a series of tools or formulas, so to speak, and some nice little limit information to help us as we work through the first principles. We're going to use the angle addition formula for sine and cosine. We're also going to use the definition of E. E is defined as the limit as n approaches infinity of 1 plus 1 over n raised to the nth power. We've seen that before. And by a quick rewriting, if we take k to be the reciprocal of 1 over n, or k equals 1 over n, let me rephrase that, what happens? Well, 1 plus 1 over n now becomes 1 plus k. N now becomes 1 over k, because k equals 1 over n. Do your cross multiply, you could also say that n equals 1 over k. And if n is approaching infinity, as we had in our first limit, 1 over n must be approaching 0. So another way of defining E, it's not the typical way that it's done, but what you see over here on the left is the classic definition of E. But in any case, E can also be defined, the limit as k approaches 0, of 1 plus k, in parentheses, to the 1 over k power. There's a few other things we're going to use. We're going to use some basic limits that the book talks about. We're going to just derive them graphically. We could have done this in the calculator, but I just went ahead and used Desmos. And there's 3 limits that we're going to look at. Limit as x approaches 0 of sine of x over x is equal to 1. That's what you see in the red graph. And you'll notice all of these 3 graphs that I built are functions that are continuous. They have no gaps, no breaks, and their limits at x equals 0 truly exist. They exist from both the left and the right side. So what you're seeing here graphically, this first function as x approaches 0, the red function, the y-coordinate sure is approaching 1. Limit as h approaches 0 of e to the h minus 1 over h, or I could do limit as x approaches 0 of e to the x minus 1 over x. That's also equal to 1, and you see that in the orange graph. In the middle, another function, cosine of x minus 1 divided by x. The limit of that function as x approaches 0 turns out to be 0. So we're going to use these different pieces, these different tools, to derive the 4 derivatives of these key functions using the first principles. So here we go. On this page, we're building the derivative of the sine of x function. First principles, sine of x plus h minus sine of x over h. The limit of that is h approaches 0. First things first, all I did is I used my angle addition formula for the sine. That's what these first 2 pieces of the equation are. And then just the rest of the difference formula minus sine of x. From here, what did I do? A little bit of factoring. I took out sine of x from this term and this term. Sine of x times cosine of h minus 1 plus our other term cosine x sine of h all over h. Next, I've broken it up into 2 limits. This is a fraction, sum, and so I just broke the numerator in 2 pieces. Sine of x times cosine h minus 1 over h, that limit, plus the limit as h approaches 0 of cosine x sine h over h. Moving forward, bit by bit, I'm going to start taking out of the limits the pieces that aren't related to h. So my first term has stayed the same. I've worked with my second term. H has no impact on cosine x, so notice that I've moved it in front of the limit. And I'm left with the limit as h approaches 0 of sine of h over h. I've also done what now in this next term? My first piece here, sine of x has nothing to do with anything as h approaches 0, so I took it out. And look what we're left with. We're left with sine of x times a limit. That's one of the limits that we saw on the prior page graphically. And look over here, I got cosine x, and I have another limit that we did on the first page. What's that translate into? Sine of x times 0 plus the cosine x times 1, and it tells me nothing more than, all said and done, that limit is cosine of x. So repeated just a couple things down here that you didn't really need to see. Same piece comes out. We wind up with what? A derivative of cosine x. So for all intents and purposes, you can just kind of ignore that last piece. But what have we proven? The derivative of sine is the cosine function. The book does a nice job of this intuitively. They take the graph of the sine function, and then they build a bunch of tangent lines on it. And they connect the dots on those tangent lines, the pointed intersections of the tangent lines with the original curve, y equals sine x. And when they do that, they notice that the shape of the resulting graph, the connected tangent line graph, looks exactly like the cosine function. Intuitive way of doing it, first principle way of doing it. Either case, the derivative of sine is nothing more than cosine x. The derivative of cosine, I use the cosine addition formula. Here's my first principles writing, no surprise. Limit as h approaches 0. Cosine x, cosine h, minus sine x, sine h, minus, first term, cosine x. All I've done is term here and here, I've written out what? The angle addition formula for cosine. From here, what do I factor out this time? Term 1 and term 3, I'm going to factor out a cosine x. Cosine x times cosine h minus 1 over h minus my last term, sine of x, sine of h. From here, what do I do next? Well, I'm going to break it into two fractions. And in this case, what have I done? I also, as I did that, I took out the pieces that don't matter with respect to h. So I can pull that cosine x out front of my first limit statement and be left with cosine h minus 1 over h. And in my second piece, sine x, sine h over h, what did I do? I can pull the sine x out because it has no impact on anything when h is approaching 0. Sine x is just good old sine x when h is approaching 0. And again, I'm in the same nice position. What do I know? This limit, based on information before, is 0. This limit, as h approaches 0, is sine h over h. Previous knowledge on page 1, using that information from the front page, gives us what? Cosine x times 0, cosine x times 0, minus sine x times 1. 0 minus sine x, negative sine x. We've just proven through the first principles that the derivative of cosine x is negative sine of x. Onward we move. Let's look at our next derivative. The derivative of e to the x with the first principles. Sorry, this is a little bit small, but again, just kind of look at your printed notes for this. Limit as h approaches 0. First principles definition, e to the x plus h minus e to the x over h. I've turned e to the x plus h into a product, e to the x times e to the h. That's the same as e to the x plus h power, minus e to the x over h, nothing new. I've then done what? For my two terms, I factored out e to the x. So I have the limit as h approaches 0 of e to the x times e to the h minus 1 over h. As we've done many other times now, e to the x has in no way is impacted by the fact that h is approaching 0. I'm going to move that e to the x in front of my limit. So I have this term now becomes e to the x times the limit as h approaches 0 of e to the h minus 1 over h. E to the x, and we prove on our first page with the graphs and those limits, this limit as h approaches 0 of e to the h minus 1 over h is nothing more than 1. The derivative of e to the x is, believe it or not, itself e to the x. Pretty cool situation. The derivative of a function winds up being that exact same function. E to the x has a lot of interesting characteristics, and that's certainly one of them. Tuck that piece of knowledge away. Next, and the most complicated of all the proofs, using first principles, is the ln of x. First principles written first. No surprise there. What have I done next? Well, it's the limit of, limit as h approaches 0. Remember, a log of something minus a log of something else, same base, is nothing more than what? The quotient of those two elements. So this becomes the ln of x plus h minus ln of x is nothing more than the ln of x plus h over x. Sorry that my parentheses got a little bit clipped here, but that's a whole fraction. So let me just go ahead and touch that up while we're here. And that'll happen in a few other places. So just be aware of that fact, just because of the limitations of my math type here. And so what do I wind up having happening? Natural log of x plus h over x. And then what I've done is I've created this as a fraction. I did x over x, which is 1, plus h over x. I broke this fraction up into what? Two individual fractions. X over x, 1, h over x, h over x. 1 plus h over x over h. Just rewrote it one more time, writing it in a slightly different manner. Limit as h approaches 0 of 1 over h. So I just kind of stuck that h out front here. The ln of 1 plus h to the x. From here, what am I working on? I have the limit as h approaches 0. Now, a new wrinkle has been added. I've multiplied by x over x. You'll see why I did that in a little bit. It's going to help us out as we build this. It's the same as building by 1 or multiplying by 1. And so let's go ahead and continue along. I now have x over x times 1 over h, the ln of what we had before, 1 plus h over x, again, as h approaches 0. So we'll keep working, see a couple new things in a second or two. So let's move on. The next thing that I've done is I just kind of broken my x over x into a couple new pieces. I've moved that x over to h. 1 over x times x over h times the ln of 1 plus h over x. Let's keep working along. And now watch what's happened next. I've just decided to bring the x over h back into the limit statement. I'm allowed to do that. There's no problem there. So I have the constant 1 over x times the limit as h approaches 0, x over h times the ln of 1 plus h over x. We'll stare down a little bit more. And now, remember, a coefficient in front of a natural log. This is the power property of logarithms. X over h times the ln of 1 plus h to the x becomes the ln of 1 plus h over x raised to the x over h power. Sorry that my type has gotten a little bit small here, but again, go ahead and look at this on your hard copy notes and you'll see that. So I'm now reduced to 1 over x times the limit as h approaches 0, ln 1 plus h over x to the x over h power. Now I'm going to do a quick substitution. I'm going to let k equal x over h. And by the way, if that's true, h over x equals 1 over k. And the nice wrinkle about this, we're using the two different definitions of e, by the way. What do I notice happens? If I let h approach 0, x over h is approaching what? It's approaching infinity. K is approaching infinity. So this whole statement I can now rewrite as 1 over x times the limit as k approaches infinity, 1 plus 1 over k, raised to what? The k power. All because k has been defined as x over h. Now, what's the nice thing? That limit is nothing more than the definition of e. 1 plus 1 over k to the k as k approaches infinity is e. So as a result, I now have 1 over x times the ln of e. And hopefully we recall the ln of e is nothing more than 1. 1 over x times 1. The derivative of ln of x is nothing more than 1 over x. So this is how we build these derivatives. Let's go ahead now and summarize. And this is straight from the book, maybe copied in a couple different pieces. We know the derivative of x to the n from the power rule. The derivative of sine x, we've now proven f prime of x is cosine x. The derivative of cosine x we have proven is negative sine of x. The derivative of e to the x is nothing more than itself, e to the x. The derivative of ln of x is 1 over x. And we're going to see, we're going to start using all these nice things in the chain rule in a few moments. We're going to be able to use these derivatives, take ourselves beyond just the basic polynomials that we've done so far. And we'll pick that up in a couple moments in our next video as we continue section 13.1. So in this video, we're just going to go ahead and differentiate some of these basic functions, continuing with section 13.1. First function to differentiate is 3 times the cosine of x. Well, remember, 3, that's just kind of a constant, so whatever we're going to have, we should have a 3 in the answer, and then we just got to figure out what's the derivative of cosine x. And if we recall from just before, and again, you have these on your formula sheet. One other thing is going to be real nice. The derivative of cosine is negative sine x. What's our answer? The derivative of 3 cosine x is negative 3 sine of x. What's the derivative of 2 sine x? Well, it's 2 times whatever the derivative of sine x is. That's one of the properties of the derivatives. We're going to have 2 times cosine of x. We have 3 times e to the x. Well, again, remember, that's just a nice little constant, so the derivative of a function multiplied by a constant is nothing more than the constant times the derivative of that underlying piece. What's our answer here? It's 3 times the derivative of e to the x, and the nice thing about e to the x is its own derivative. Our answer is 3 e to the x. 13 ln of x. I hope you're not too surprised that that's going to be 13 times 1 over x. Again, hopefully some pretty basic stuff you're starting to see now. Can we do some problems evaluate a derivative at a location? I bet we can. Let's give it a shot. Find the derivative and evaluate it at the specified x coordinate. Our function is f of x equals 3 sine of x. We're going to evaluate it at x equals pi over 4. 3 times, what's the derivative of the sine function? It's cosine. Our derivative is nothing more than 3 times cosine of x. We need to evaluate this where? At pi over 4. F prime evaluated at pi over 4 is 3 times the cosine of pi over 4. And if we kind of remember our unit circle, that's the square root of 2 over 2. F prime of pi over 4 is nothing more than 3 times the square root of 2 over 2. F of x equals 4 times cosine of x at x equals pi over 3. Our derivative is 4 times derivative of cosine, negative sine. Negative 4 sine of x. Plug in pi over 3. 4 times the sine of pi over 3. And if we remember a little bit of stuff from the unit circle, we'd realize that the sine of pi over 3, let's take a look and see what this will happen to be. Sine of pi over 3, which is 60 degrees, relatively high y value. That's going to be, oops, as my marker goes a little bit bad here, negative 4 times the square root of 3 over 2. I'll have negative 2 the square root of 3. So negative 2 the square root of 3 is what I'll see here for an answer. Again, why? Negative 4, 60 degrees on the unit circle, relatively tall in quadrant 1, x coordinate just 1/2, y coordinate square root of 3 over 2. Sign on the unit circle goes with the y coordinate. Negative 4 times the square root of 3 over 2. Negative 4 over 2 becomes negative 2. Negative 2 the root of 3. Tangent line problems are also something that we should be able to do. Now I'm going to have this one written all the way out just to save ourselves a little bit of time. Find the equation of the tangent line to the function y equals 2 e to the x at x equals 1. Well, first things first. What's y prime? What's the derivative of this function? It's 2 times the derivative of e to the x, e to the x. It's 2 e to the x. I need to evaluate my derivative at x equals 1. So f prime at 1, remember f prime I can call this f of x if I want to. F prime of 1 is nothing more than 2e to the what? First power, or 2e. I now know the slope of my tangent line to the curve y equals 2e to the x at x equals 1. It's 2e. When x is equal to 1, let's evaluate the function. F of 1 is 2 times e to the first, 2e. So our point that our tangent line touches, this tangent line that happens to have a slope of 2e, goes through the point 1, 2e. What's the equation? Excuse me, let's fix a little handwriting here. Equation of line with slope 2e through the point 1, 2e. Well, I can say 2e equals 2e, our slope, times x, 1 plus b. 2 equals 2e, b equals 0. What's the equation of our line? Y equals 2e times x. That's not 2e to the x. Be careful here. It's just 2, the number e, times x. So one more piece of legwork to do, and we're going to do this on the next couple pages. Take a look at the function f of x equals 2 sine x. We're going to take a look at the function f of x equals negative 3 cosine x. We're going to go ahead and try to derive the stationary points, identify some max and mins. You know, because of the up and down, the periodic nature of these functions, you could probably graph these things pretty quickly. You'd realize that they have a midline of 0. They have an amplitude of 2. Makes me think, hey, the max value I'm ever going to see for 2 sine x, and that problem is going to be what? 2. A min value is probably going to be at negative 2. And since we know how to draw these, we could probably figure all this out just with a quick eyeball inspection. It wouldn't surprise us too much that what? Amplitude of 3 for this function, midline of 0. It's not going to be too surprising that the max y coordinate is going to be positive 3. The min y coordinate is going to be negative 3. But let's do it through calculus and verify these stationary points and where they are. So here we go. F of x equals 2 sine x. Already kind of said this piece. We could inspect this by hand, but let's go ahead and do it with calculus. What's the derivative of 2 sine x? It's 2 times cosine x. How do we find stationary points? Set the derivative equal to 0. 2 cosine x equal to 0 requires what? That cosine x will be equal to 0. We're solving all these, by the way, on 0 to 2 pi. So where does this happen? 2 cosine x equals 0 when cosine x equals 0. Cosine x equals 0 will be true at x equals pi over 2 and at x equals 3 pi over 2. That's our stationary point x coordinates. Let's get their associated y coordinates. So what do? We evaluate f of x at pi over 2. We evaluate f of x at 3 pi over 2. 2 times the sine of pi over 2, 2 times 1, 2. That critical point or stationary point is located at pi over 2, comma 2. When we evaluate the original function at 3 pi over 2, 2 times the sine of 3 pi over 2. Sine of 3 pi over 2 is negative 1 from our unit circle days. 3 pi over 2, negative 2 is our other point. We certainly expect, working from our intuition, that what? There's a max and there's the min. Let's prove it through a sign chart. Kind of a tedious method, but no problem. So I've done a sign chart, kind of walking through the different quadrants you might have noticed. Quad 1, quad 2 and 3 when we run between what? Pi over 2 and 3 pi over 2. And then 3 pi over 2 to 2 pi, quadrant 4. What do I know about the derivative 2 cosine of x? What do I know about the sine of that derivative? Well, in quadrant 1, 2 cosine x is positive because cosine is positive. In quadrants 2 and 3, when x runs between pi over 2 and 3 pi over 2, notice I use the word between. There's no equalities here. What do I know happens in all those cases? 2 cosine x is a negative number. Is that helping to me? Did I just go from positive to negative? I sure did with the derivative equal to 0. I've just shown through calculus that pi over 2, comma 2 is a maximum. Going back over to quadrant 4, what do I know about the cosine function? It's going to be positive. So 2 cosine x, when x is between 3 pi over 2 and 2 pi, is going to be positive. Look what my function's done here. It's gone from negative to positive with a derivative of 0 right in between. What's that telling me? It's confirming my suspicions that 3 pi over 2, negative 2, represents a minimum. Now, if I was so inclined, what's another way in which I could do that max-min test? I could run the second derivative test. Well, f prime of x, we said was equal to 2 cosine x. F double prime, the second derivative must be equal to what? 2 times the derivative of cosine x, negative sine x. Negative 2 sine of x. So now, let's evaluate it. Where? At the places where the first derivative was equal to 0. When the first derivative was equal to 0, the first point we saw was at pi over 2. If we evaluate the second derivative at pi over 2, we get what? Negative 2 times the sine of pi over 2, we get negative 2. This is what type of value? It's a negative value. First derivative 0, second derivative decreasing, we have a maximum. Do the same type of work. Evaluate the second derivative at 3 pi over 2, negative 2 times the sine of 3 pi over 2, negative 2 times negative 1, there's a 2, a positive number, we have a min. So two different methods, second derivative test, first derivative sign chart, both of them useful in determining what? Whether we have a max or a min. And we've now identified those suspected points exactly for what they are. Same type of work for f of x equal -3 cosine x. I take the derivative, -3 times negative sine x, 3 sine x. I want that equal to 0. How can I do that? I need sine of x equal to 0, which happens where? When x equals 0 or x equals pi. So, what do I do next? Go ahead and evaluate the two functions at those critical x values. F of 0 is what? -3 times cosine 0? -3. 0, -3 is a point. I suspect that's a min. F of pi is what? -3 times the cosine of pi. -3 times -1, +3. Pi 3. I think that's going to be my max. Again, we'll spare the sign chart this time. Let's just do a second derivative test. What's the derivative of 3 sine x? It's 3 cosine x. Second derivative is 3 cosine x. Evaluate the second derivative at the values of x where the first derivative was equal to 0. That's all about what the second derivative test is. So, first place, x equals 0. The second derivative evaluated at 0 is 3 times the cosine of 0. It's 3. It's a positive. We have a min at what? 0, -3. Evaluate the second derivative when x is equal to pi. 3 times the cosine of pi is -3, because the cosine of pi is -1. We got a negative second derivative when we had what? 0 for the first derivative. What's that tell us about this point, pi over 3? It tells us we have a max. So this is section 13.1. A lot of stuff, a lot of proofs or whatever. Fortunately, we don't really have to focus on the proofs, more just on the practical. Your formula sheet gives you all these lovely derivatives. You will have them on your formula sheet. That being said, knowing them, remembering them, being good to use them, will help you certainly in future months, weeks, and years. But for the moment, the formula sheet will be a good lightning rod for us.